Welcome back. In the previous lesson, what we've covered is in multiple regression as well as feature importance. The video before that, we covered multiple regression along with stats model. In this video, we're going to take a moment out and understand the underlying estimation method that is used in machine learning. Instead of going through the normal linear algebra to actually calculate the actual estimates or optimize to find the actual estimates, by and large, most of machine learning as well as deep learning make use of gradient descent. There is a variance of this called stochastic gradient descent, but in this lesson, we're just going to cover gradient descent. So I'm just going to walk through and go through this lesson with you. Now, this notebook is inspired by Chris McCormick's lesson on his blog on gradient descent derivation. So just a little bit of background. Now, typically when you look at linear regression, you have y or hx here, or the function x is equal to, this is the intercept term plus a coefficient multiplied by the independent variable. So you try to find the values of the beta 0 and beta 1, in this case is theta 0 and theta 1, which provides the best fit of our hypothesis to our training set. Ultimately, you try to minimize the actual difference between our prediction and the actual value. The training set examples are labeled in x and y. X is the input value or the independent value, and y is the output or the target value. So let's walk through the mean square error cost function. This is what is used to actually to calculate your estimates, and this is what it looks like. So at the core of the mean square error, this is what you have is the algorithmic prediction for the ith training example using the parameter theta, and this is what we observe. So what you have is this term minus the actual. This is the estimate, this is the actual, and then the whole thing is square. So what you have here is the error term, and this is the square of the error term. And what you have, 1 over m here, because we have m observation, that gives you the average. The other term for average is mean, so hence the term mean, and the whole thing is square, and the inside is really the actual error term itself. And typically, cost function is denoted using J. So the actual details or the so-called notation used is all listed here. The mean square error measures the mean amount that the model's prediction deviate from the actual correct value. So this is really the error. It is a measure of the model's performance on the training set. The cost is higher when the model is performing poorly on the training set. So the higher the cost, that means the model performed poorly. The objective of the learning algorithm is to find the parameters theta, which gives the minimum possible cost j. So ultimately what we're trying to do is minimize that. Hence this function here, minimize the j theta or the cost function. I'm going to go through a couple of examples here. Example 1 here is gradient descent minimization. It's a little bit difficult to understand these mathematical notation for most of us, so I'm going to use an example, a simple one, to help develop the intuition. Now let's assume our cost function is theta square, so this whole thing here is actually theta square, and we want to find the value of theta which minimize theta, the cost function. So let's assume we start with theta is equal to 3. Now, gradient descent is basically an iterative algorithm which we will run many times. Now, on each iteration, we apply the update rule, which is this one here. Basically, this colon equal symbol means replace the theta with the value computed on the right. So once we actually calculated this whole thing, we update this. So it's theta minus alpha. I'll come to what alpha is in a minute, and multiply by the derivative of cost function. Alpha is actually the learning rate. For now, we're just going to assume 0.1. So the derivation of derivative of the cos function in our case here is 2 theta, because it's theta squared, so you bring the 2 down and reduce the power by 1, so hence you get 2 theta. Now let's apply this to an example. We import the basic things that we need. Remember that we're going to start theta with 3, alpha here is 0.1. We set up the data. This is basically an empty list. Okay, so let me change this. This should really be not be hard coded. So we're just going to iterate through from 0 to 10, or range of 0 to 10. Basically we'll stop at 9, including 9. The result here is alpha multiplied by 2 multiplied by theta. What is this? That's basically this portion here. So this is alpha multiplied by 2 multiplied by theta. So this portion, this 2 times theta here, is basically the derivative. Alpha here is actually this term here. So that's our learning rate. So this part here is really printing the actual result of each theta, starting from 3, followed by what the actual result is from this, and we repeat. And we store the actual value of theta as well as theta squared. What is theta squared? Theta squared is our original cos function, and so that we can actually print it out later. And we update theta accordingly. Theta is equal to theta minus this result, which is this portion here. So we will run that. Notice that we start with 3, and the theta square is a 0.6, and on it goes, and it gets updated. Notice that theta minus 0.6 is 2.4, and repeat. So I'm just going to store that into a data frame, pandas data frame, for easy reference. And here what we're trying to do is plot this out. We're just going to plot this out in the space of -2 all the way to 4, break it into 100. And we're also going to plot the x. This is the x and this is the y. This, if you take notice here, is actually x squared, x to the power 2, which is our theta square here. So in essence, we are plotting the cos function. This is the x, and this is the x squared, or in our case theta square. And we're going to plot the scatter plot of this temp, TEMP, and with the marker of x, and with the label of x is being our theta and the y label being our cos function. Okay, if you have a look at this, this is basically our theta, and this is our cos function. This is actually our cos function, which is theta square. Notice that as we start learning, remember we start learning from 3, okay, 3 theta of 3, and this is the theta square. Our learning went from 3 to 2.4 to 1.92, from 3 to from 3, which is 3 here, 3 to 2.4, and on the way all the way down, and eventually it will end up with 0 being the minima. So that's really how the gradient descent function works. In essence, what you're doing here is that you feed this, and then you take a negative of the learning rate multiplied by the derivative, and then you update theta, and basically it's a iterative or continuous loop until theta is 0 or close to 0. So that's basically how that works. So I'm going to show you a second example here. Now notice that the cos function is a little bit different this time around, is theta to the power 4 plus theta square, and the derivative is 4 theta 3 plus 2 theta, and the actual update function here is basically theta minus the learning rate multiplied by the derivative itself. So I won't go through all of these. I've updated with all of the relevant information, and I'm just going to show you what this looks like. Notice that the theta to the power 4 plus theta squared curve looks like this, and this is our learning rate. Notice this is our so-called the speed of the learning, starting from here and going all the way down. So that's really how you actually implement gradient descent, okay, for learning the actual theta itself, or the coefficient itself. So having that background, I've also showed how you can actually derive the cost function, starting with the cost function. So this is the derivative of the cost function. So it's a step-by-step process. Typically, you start this way, and you take a derivative of that, and you ended up with this. So I just want to highlight this is the actual derivative of the cost function. You bring the 2 down, hence it's actually 2 here. Actually, this shouldn't be 2 here. It should be 2 on top. Okay, and followed by the inside. This is reduced by 1, and when you derive or calculate the actual derivative of this, you get the xi on the outside. And the update rule again looks like this. Once again, this shouldn't be that. There should be 2. All right, so notice that this is a bit irritating. It actually, well, it's a bit untidy, let's put it this way. But nevertheless, this is, if you start off with the cost function, this is the actual derivative. And when you substitute the derivative into the update rule, and this is what it looks like. So if you simplify everything, basically our gradient for the coefficient x is just the average of our predicted values multiplied by their respective x value. So the average of the predicted values is this portion here. So this is the average, but the 2 kind of ruin it. Multiply by their respective x, which is this one here. Now quite often you actually see a slightly different form of the cost function. There is actually a 1/2 instead of 1/m. The reason being, when you bring the 2 down, when you actually calculate the derivative, 2 with 2 cancelled out, and you get a nice and neat function. Hence the reason why people start off with 2 for the cost function. Right, so we're going to apply this gradient descent to the Boston housing data. We import the Boston housing data, and we're going to conduct this using the LSTAT as well as the actual y itself, or the target value. In our case is the median housing value. And we're going to perform standardization and transform our x and y so that it's actually standardized. And we'll cover what standardization from min-max and also normalization means in the future lecture. For now, just take it that we're gonna standardize it. Okay, so coming to the so-called gradient descent part, we set the alpha to slightly smaller, 0.0001, and basically this is the w itself. The cost function, we set it to an empty list. Iteration is 100. So we loop through this. Let me just highlight the actual so-called what this iteration is trying to do. This is calculating or predicting y, and this here is calculating the error. So these 2 terms, if you come back here, is in essence this portion here. The first term calculates the or predicts the y, and the second term is actually calculating the error itself, which is what this is. And these 2 terms is basically updating using the so-called update rule, okay, to actually update our coefficient. So what you have here is the alpha multiplied by x times the errors. So what you have is x, so alpha, so this is your alpha, all right, and then you have your x multiplied by the error. So in essence, that's really what this 2 portion is. And finally, this is the actual cost itself to the power of 2, sum, and then divided by 2. So that's really the whole process of updating the gradient descent, and keep repeating until you actually come to the minima itself. So let me repeat again. This is the alpha multiplied by the x multiplied by the errors, and this the cost function is the error to the power of 2, sum it all up, and then divided by 2. Okay, so let's run this and we append the cost and then we plot that out, and this is what it looks like. So in essence, our sums of squares of errors decreases as we run through more and more epoch. As we continuously run our training, the actual sums of square reduces until we find pretty much the lowest point in terms of our errors. So that's really the end of this lesson on applying gradient descent to estimate the actual coefficient itself. Although I didn't show you what the coefficient itself, it's quite easily done. So it's W underscore here, which is these ones here. There you have the W0, the intercept, and this is the actual beta 1. So that's the coefficient or the slope for LSTAT by itself. Now, having done all that, I know that if you don't actually make an attempt or haven't any practice, you won't master this. So what I'm going to do now is that I'm going to give you a simple assignment to perform this same process on RM, okay, and see what it looks like. That's the first exercise I want you to do. The second exercise I want you to do is try reducing this to 0. I think it's 0.1 that we use here. Yep, 0.01, and see what actually happens. And when you plot it out, notice that it actually exhibits explosion. Instead of going down in terms of your sums of square error, it actually explodes. Well, actually I've kind of given the answer away, but I'd like you to actually try that out with the RM, and also see at which point, at what rate of alpha does the actual so-called gradient descent estimate explode rather than converge to the minima or 0. With that, I'm gonna ask you to pause right now, and once you come back, I will summarize the lesson. Welcome back. I hope you've actually made an attempt on utilizing this whole thing on RM and alter the alpha a little bit, and just to see what it looks like. The whole exercise is quite straightforward. Instead of LSTAT, I can just change it to RM, and I get similar curve here. Of course, the estimates of all the slope will be slightly different. So I'm going to leave that here, and I'm going to also save this Jupyter notebook for you to refer to play around with it until you get familiar and compare it with what you actually have done. I hope you found that lesson useful to understand what gradient descent is and how it is applied in the estimates of your coefficient. So I'm going to end here. Thank you for paying attention. In the next video, we're going to go into regularization method for regression. I look forward to seeing you in the next video.